Hello, good evening. Can you hear me and can you see the screen?
Yes, sir.
Yeah. Last week, I just saw in the chat section there was some discussion. Some people attended the class. I mean, came into the classroom. I told no that I will not be taking the class on 25th, and the 25th class I took on 19th.
Yes, sir.
Yeah. No, I saw you also commented there that the class was supposed to be here. But you are the only attendee in the 19th class. So
Yes,
I
sir.
just
Actually, I forgot. There was
okay.
email message, no?
Yeah,
It
that I
is
saw. They sent a
plus.
message. I don't know why. They sent a message. I saw. Anyway, I was outside India last week. So, all right, we'll wait for some more time. and then we'll start. So this is the last week for induction motor. I mean, I thought there will be a larger chunk of synchronous machine, but that is not the case. Today also we'll be solving problems on induction motor, mostly induction motor starting. And the 10th week, and there are 2 more weeks, and the
Yeah,
rest two
in
other two
these
weeks are
problems, na sir, actually
yeah,
facing difficulty
starting.
that is starting. So if you, it is
Okay.
possible for you, you can draw the diagram where we are
What
calculating the
diagram?
currents and all. It will
Starting,
help a lot.
see, one type of starting is rotor resistance starting. I think last 2 weeks we concentrated a lot on rotor resistance, isn't it? That if this is the torque speed characteristic, if this is the natural characteristic, and then if you add rotor resistance, then what happens is the peak torque remains the same, but the sleep at which the peak torque happens, that reduces. That is, the peak torque happens at lower, sorry, that increases. So the peak torque happens at lower and lower starting speed. Sorry, lower and lower speed. So it is possible now, since alpha, that is the sleep at which the full load torque occurs, that is given by what? R2 by x2. R2 by x2. So if you want the starting torque to be maximum, then you can put a calculated value of R external such that R2 becomes equal to x2, and you get alpha equal to 1, and your starting torque looks something like this. So your characteristic looks something like this. Okay. And the objective of starting is to reduce the starting current. Let's say, for example, a DC machine, when you are starting, the back EMF of a DC machine is proportional to speed. So at starting, the back EMF is 0, and you have a huge starting current if you give the full voltage. Similarly, for an induction machine, this is the rotor circuit, and this is R2 by S x2. At starting, what happens? At starting, S is equal to 1, and when the speed increases, S reduces. That is, R2 by S increases. So the minimum resistance of this circuit is at starting. That's why it draws a large current at starting. Now, increasing the rotor resistance not only mm, increases the starting torque, it also reduces the starting current. True. So this is one potential way of starting. First thing. Another way of starting is a simple, like what we do in um, DC machine also, armature voltage control, or you can also say auto transformer based control, auto transformer based starting. Now there are what to say, inferior methods also, where you put inductance or resistance in series. Obviously they are inferior, because if you put resistance in the series, that means your overall efficiency is reducing, and if you put inductor in the series, your efficiency is not reducing, but your power factor is reducing. Okay. And reduction of power factor actually leads to reduced efficiency, because you are drawing large current, but you are not getting that much torque. Okay, that much active power. So that is in one way also a reduced efficiency. So that is one way of starting. We have several problems today. One problem studied on auto transformer starting, and the other one, I think there are other methods also. If you go through the books, let me see, auto transformer starting.
Star delta.
Yeah, star delta. I will just check if there is anything else. Okay, this doesn't have. There is a star delta. Star delta starting is a very case specific starting. Only an induction motor which is designed as a delta induction motor, you can start it as a star induction motor. The other way is not possible, obviously, because if it is, say, you have a 400-volt induction motor which is delta connected, designed to be delta connect, designed as a delta connected induction motor, that means every winding is rated for 400 volt. Okay, now if you start as an delta connected induction motor, at starting all the windings are getting rated voltage. Now same induction motor, just by changing the connections outside, if you start as star connected motor, same machine, just changing the connection, you need all the 6 terminals outside the motor, then only you can do this. Then what you will get is 400 by root 3, that is 230 volt. So you are reducing the voltage in this fashion, and so your currents are reduced. But it's a very case specific. The other way is not possible. A normally star connected induction motor can be start as a delta connected motor. Okay, that will be dangerous, hazardous for the machine. And the most crude way of starting, which some induction motors are designed for this, which is DOL, direct online starting. Okay, all these types of startings are there. Now the basic theory behind starting is the relation between the torque and the voltage. Now if we ignore the stator impedances, then what we are left with is this. Okay, this E2, you can say, is almost equal to the supply voltage V, or equal to, if you completely neglect, only V. And you have here R2 by S X2. Now let us call this thing as Z. Okay, Z equal to R2 by S plus J X2. Okay, so now what you have is the torque. Torque is, we know, air gap power by omega S. So what is air gap power? Air gap power is 3 times this voltage V into current E2I2 or VI2, whatever you write. And E is a, and sorry, E you keep E2, and I is E2 by mod of Z. So what you get is E2 squared by omega S mod Z. So what we are getting is, for the induction motor, under a certain, see, one thing you must notice here, torque at a given slip is proportional to voltage squared. Okay, because I have taken Z as a constant, so Z as a constant means slip is constant. That means at a certain speed or certain slip, the torque is proportional to voltage squared. Okay. So if this is torque, this is speed, with reducing voltage, it reduces like this. Okay. Now that is the whole theory behind this. So when we have auto transformer is simply like this. If you have tapping at X, and if you have V1 here, then what you are getting is V X V1. this much. So your starting torque at DOL, let us say, and starting torque when you are starting with auto transformer, that is proportional to L at V voltage DOL, so full load voltage or supply voltage, that is V1 by X V1 whole squared, that is 1 by X squared. So starting torque with auto transformer is tapping ratio, whatever this X is, X squared times that with DOL. So torque will be reduced by this much. And if you look at the current, see, this, we are talking about starting, so the Zs is the same in both the cases. So the current I, which is E by Zs, starting current Is. So starting current at DOL by starting current at auto transformer starting, the voltage is 1 by X. So current will also be 1 by X. So starting current at auto transformer starting is X times uh, that of DOL. Now you notice here one thing. I did this using the rotor circuit. I simply used the rotor circuit here, and I said that this voltage is reduced by X times, so the current is also reduced by X times. Now if you look here at the auto transformer, and suppose a current of X times ISDOL is being drawn, okay, then by energy conservation, the current that is being drawn here is X squared
Sir,
times IS, yeah, DOL.
yeah, this is the current that is from auto transformer.
And which one?
That X
Yes,
time of the
that
DO.
is that is
Now the current
motor
from the
current.
line side.
No, it's the motor current or transformer. That's why I'm drawing in the secondary side. X times ISDOL.
Yeah,
Now
yeah,
the
that is
line current is, you will multiply with the translation, that X comes. So X square times IDOL.
okay. Okay.
So from the line, if you see, starting current with auto transformer is X square times um, starting current with direct online. X is obviously less than 1 from the diagram. So we are getting a reduced current when we are starting with auto transformer. Our current is reduced by X squared times, our torque is reduced by X squared times, and voltage is reduced by X times. Okay, so this is auto transformer starting. And star delta starting, if we look at, it's even easier. So let us say the line voltage is V. Line voltage is V. Or the, sorry, let that also be the rated voltage of the machine. So star delta starting is always DOL. Okay, it's there is nothing else between the motor and the supply. Maybe the switching circuitry is there that switches from delta to star and all, but no other impedance is added. Okay, so now if this is V, now at starting what you are doing is, at starting phase voltage is 1 by root 3 times V. Say I call this VR, V rated. Okay, So 1 by root 3 times V rated. I will mark this as star delta starting. So V phase is 1 by root 3 times V rated. So if that is the case, then uh, what is I phase at starting? At starting, I phase is also 1 by root 3 times I rated. When I say I rated, I mean I rated starting. Means if this delta connected induction motor, if I had started this with DOL, then the current would have been IR in the phases. Now, since the voltage is 1 by root 3 times, so the starting current in the phase is also 1 by root 3 times. Now, here look one thing, at starting, if the current here is IR, then this current is root 3 times IR, right? But when the combination is star, then whatever the phase current is, that is the line current, right? Line current, right? So now if I compare the at the line side the starting current with delta and the starting current with star, starting current with delta is root 3 times higher, and starting current with star is 1 by root 3 times IR. So this becomes 3. That means starting current with star is 1/3 that of delta. So you are reducing the current by 1/3. Now, since the current is reduced by 1/3, torque is also reduced by 1/3. Or you can say it from the voltage also. Torque is proportional to voltage squared. We saw star delta. And nothing to say about DOL, rotor resistance starting we discussed a lot for the last 2 days. Yeah, that's all. Any question?
Solve, na? Then we will come to know more.
Okay.
Yeah.
So it gives a motor with 18 kilowatt, 380 volt, line to line. Obviously, again, this gives me a lot of frustration when someone mentions this in a BTech course. It's the first year thing. Line 3-phase voltage means line to line if nothing is mentioned. Oh, anyway, 18 kilowatt, 380 volt, 3-phase squirrel cage induction motor has full load efficiency of 81% and a power factor of 0.76. Okay, the full load current is 22% of the starting current. Understandable. The full load torque is 70% of the starting torque. So if I just want to have an idea how the torque speed looks, so full load torque is less. So this is the starting torque. Let us say this is the full load torque. So the machine characteristic looks something like this. This is the full load torque, the starting torque. Okay. Now, to reduce the starting current, autotransformer starting is used with a tap setting such that we get full load torque at starting. So basically, we are trying to get full load torque at starting. We are trying to get TFL at starting. Naturally, we get TS. Now we are trying to get TFL. Now, full load torque is 0.7 times that of starting torque. So we want to reduce the torque by 0.7 times. So we have to reduce the voltage. So we'll write again. Now let us not write like this. This is what it is. it is given. Now we are doing auto transformer starting. Okay, so two cases. So T starting with say DOL by T starting with auto transformer. Okay, now what is given? Auto transformer starting is used such that we get full load torque at starting. Full load torque at starting. That means we are reducing this by 0.7. So this is what? 1 by 0.7. Yeah, is 1 by 0.7. And this is equal to the supply voltage, say the rated voltage V, and the reduced voltage XV squared. We know torque is proportional to voltage squared. So from here, what do we get? We get X squared is 0.7. So X is square root of 0.7, which is 0.837. So 83% tapping is required to get full load torque at the starting. Is it understood?
So like this is given the full load torque is 70% of starting torque.
Yes.
So how you take this full load as a the direct online starting torque?
No, full load torque is not direct online starting torque. See, you look at the torque speed characteristic first. There it is under. Now how do I know the torque speed characteristic is like this? I know from mm, this statement: full load torque is 75% of the starting torque. So full load torque, you see, I have shown lower than the starting torque. This is understandable.
Yeah, yeah.
Okay, now this curve is natural. This curve is natural, or also you can say DOL. Now we are doing an auto transformer starting such that the curve is like this. The curve is like this. Let me draw the curve properly. Understandable?
Yeah, you reduce the
The
voltage.
curve is like this. So I am reducing the starting torque by 70%. I am reducing the starting torque by 70%. So if the starting torque is reduced by 70%, that means the voltage squared is reduced by 70% because torque is proportional to voltage squared.
Yes.
So that gives me this equation. Clear now?
And there is written a circuit we get full load torque at starting.
That's what we are getting. No, this red one is
No.
the auto transformer starting.
Okay, so this full load torque we want to get at starting.
Hmm. Means basically what they mean to say here is such that we get the rated. Now obviously when you are starting with auto transformer, if you do not remove the auto transformer after the machine has started, at that condition its full load torque has also reduced by 70%. So thing is, the starting torque I want equal to the rated full load torque. That means I am reducing the starting torque by 70%, or I am making the starting torque 70% of the DOL starting torque. So my voltage squared should be 70%.
Yeah, okay, sir.
Yeah. Okay. The next question is Estimate the line current drawn by the motor from the auto transformer at starting. Line current drawn by the motor. Okay. So what do we have? We have the full load current is 20% of the starting current. Okay. Now these two are natural. These two statements, they are natural characteristic. Okay. Now let us find out what is the full load current. Full load current is 22% of the
From the
starting
power we
current.
can get.
Yes. Now I already mentioned that this power that we show here, this is output power, right? This is output
Yeah,
power. So input power is how much? Input power is output power by efficiency. By efficiency,
0.81.
0.81 input power. This is equal to root 3 times VL times IL times cos phi. Okay. Now if you solve this, what are we getting as a line current? Should be somewhere close to 44.43. True. Now this is the full
55.
load line current. How much?
55.
55. Let me do it once again. 18 kilowatt by 0.81 times root 3 times 380 times 0.76. No, 44.425.
Mhm. Yes, sir. 44.
Okay, so this is the full load line current.
So we can get starting current from dividing by this. No?
Yes, full load line current. Now, full load line current is 20% of starting current. So 20% of starting, sorry, so this is 20% of that. So
4
40.443
times.
by 0.22. Yes, more or less 4 times, you can say.
177.
Huh? 201. 0.22, there is a lot of difference. Let's check once. 201.9 ampere.
4.22.
So as of now, whatever we have done is all for DOL, direct online starting. Okay, because these are all natural characteristics. Now we have added the auto transformer. Question is, what is the line current drawn by the motor? So it is asking for the secondary side current. So it's simply I starting using the auto transformer. The voltage is X times, so the current will also be X times. So X is 0.837 times that. So this should give you
169.
168.95 ampere. Yeah. So this is the current that the motor draws from the auto transformer. Now line current drawn from the supply mains. So again another X will be multiplied.
Mhm.
So line current at auto transformer starting is another X times 68.95. That is 141. Okay.
Yes, sir.
Now the question is estimate the line current that would be drawn from the supply means if we use DOL starting. You already did that. DOL starting supply main current is 201.9 ampere.
You said 20201.
Yes. So is it understood? This is one problem on this auto transformer starting.
Yes, sir.
Okay. So next one is a three-phase 380 volt 18 kilowatt squirrel cage induction motor with efficiency 84%, power factor 0.75 at full load. Motor is supposed to be delta connected during the full load operation. The starting current at the rated voltage is 7 times the full load current. Estimate the line current in ampere drawn from the supply at starting if dual is used. Now this is straightforward. We have to first find out the rated current. So rated current is 18 sorry kilowatt output by 0.84, that gives the input is root 3 VL I full load times what cos phi. So then what is the value of full load current? Is it 43.41 ampere? Now
Yes, sir.
since this question is a clearly it is going to be a star delta starting question, so do not mess up with the phase and line currents. Okay, keep that in mind. So this is obviously line current because we have written this root 3 VLIL cos phi, right? Line current. Now uh, what is the question? Estimate the line current at starting. Okay, so it's given that starting current is 7 times the full load current, so it is 7 times IFL. How much is it? Should be somewhere around this. Okay. Now the question is estimate the line current drawn from the supply mains at starting if auto transformer starting is used with the tapping at 55% voltage. So we already derived this, that the current becomes x squared. Okay.
Yes.
If you are unsure about all these things in the exam, do not use the formulae where which is x squared, which is x. Simply do it step by step. Auto transformer tapping is 55%. So the starting current at the motor end becomes 55%. That is the motor end, secondary side of the auto transformer. Now the primary side, another 0.55 comes because of the turns ratio. So this is the line current at starting if auto transformer is used. How much is it?
Yes, sir. It is x square IDUL.
Yeah. Somewhere close to 91.92 ampere. Okay. Next question is estimate the line current drawn from the supply mains at starting if star delta starting is used. We derived this. What did we derive? The current becomes one third. The current becomes one third because what happens is the voltage becomes one third. So the phase current becomes one third. Now, since in delta, the line current itself is root 3 times the phase current, another 1 by root 3 comes. So it becomes one third. We have derived that. So starting current with DOL and in star connection, that is one third that in the delta connection. 303 times 87, 101 ampere it will be. Clear?
Yes, clear.
Okay, just a minute. Yeah, so now that is done. The last question today. Yeah,
This is easy, sir. This one. This.
this one. Okay, we have to complete this anyway. So we'll do
Mm.
a three-phase squirrel cage induction motor has per phase rotor resistance this, per phase rotor reactance this, negligible stator impedance current. So the motor is supposed to be delta connected for full operation. Let Tmax with the maximum torque obtainable under delta connection rate voltage. Okay, so then in the natural characteristic, Tmax is the maximum torque. If we use DOL starting, then estimate the ratio starting torque by Tmax. We're using DOL starting, so just a minute. Starting torque by Tmax. Okay, so as of now, there is no trickery with starting. We simply have the starting torque by peak torque as 2 alpha by alpha squared plus 1. Alpha is R2
.075.
by x2. How much?
0.075.
0.075. Okay. So how much is it TS by TP?
Yeah, one point.
Is it 0.149?
0.149.
Okay. So this is what they have asked. Starting torque by peak torque or max torque. Okay. Okay. If we use star delta starting, then estimate the ratio of starting torque by Tmax. See, if the starting is star delta, then uh, okay, starting torque by Tmax. Just a minute. It should be the same. Should be the same? No, just a minute.
It's a one third.
One third. Yes. Oh, okay. Tmax is not this Tmax. Tmax is the previous Tmax.
Yes.
Sorry. The starting torque by Tmax, if you consider, say when you are say when say suppose this one is the characteristic for star and this one is the characteristic for delta. That something like this. Let me draw the other way. Yeah. For delta, this is delta, this is star. Now these Tmax they are considering. If you take, see, for any characteristic you do in this way, starting torque by Tmax ratio will be the same because 2 alpha by alpha square plus 1 is the same. But what they are doing here is comparing the starting torque with the previous Tmax. Now starting torque has become one third, so the ratio will become one third. Understandable, no?
No, what you were saying, sir, it will remain
What
the
I'm
same.
saying is, see, they are using now star delta starting. Then estimate the ratio starting torque. This starting torque is star condition. This Tmax, as they have defined in the question, is in the delta condition. It is not the ratio of starting torque in star condition by maximum torque of star condition. In that case, it would still remain the same 0.149 because alpha is not changing. But they have defined Tmax as the maximum torque obtainable under delta connection. So Tmax remains as usual as before, what was in the last problem. Starting torque is
Okay.
one third. That's why this ratio is becomes one third. Tmax is a constant here. Tmax is not the maximum torque in star. It's still the delta condition, whereas the starting torque is the star condition.
Yes, sir.
Yeah, that's why this question comes like this. Okay. All right. Now, if we use auto transformer starting, estimate the ratio starting torque by Tmax. So auto transformer, what happens? We have seen it becomes 0.75%. So square of that. So again, this ratio times the square of the tapping percentage. This should give 0.0839. Okay, so that's all problems for today. If you have more questions, you can ask.
Delta star, na sir. This
What?
the delta star, the motor
Mm.
current is like 1 by root 3, where we are
Yes.
assuming that a delta.
Hmm.
Because the
You should
phase
not say
current
motor current. Call it
it is a line current. Is
the
coming
phase
from
current is one
outside
by
the
root
motor.
three. Yes.
And then on one, then we are because voltage is 1 by root 3, so it becomes 1 by 3.
No, the phase voltage becomes one by root three. So the phase current also becomes one by root three times.
Yes.
Okay. Now star
Mm.
connection, whatever the phase current is, that is the line current. But delta, the line current is root 3 times the phase current. So two
Yes,
root
sir.
3
Yes, sir.
factors are coming into play. So the current becomes one third.
Mhm. Yes, sir. Okay. Thanks.
Yeah.
These are very old techniques, no, sir?
Yes, you can say. I think in some industry they still star delta. I do not know, but variax there might be.
The star delta generally जो residential buildings they use for the water pumping on.
Oh, okay.
Some uh, floor means they use star delta to start big motors.
Hmm. Okay.
But now the VFDs, they are variable frequency drives.
Now we means all static controllers,
Yeah,
all kind of
electronics,
static
yeah, power
controllers. Yes.
electronics is there.
Hmm. Okay, I'm not going to discuss anything more today. If you have any questions or maybe someone else joins, I will wait for them.